Hi, everyone. I just wanted to start off by introducing myself. My name is Danya, as Aisha said, and I spent the summer working on a project that was a little different than anything I've done before, but I was looking at how to construct a lab-scale model of how a glacier flows. So to start off, I wanted to just show the satellite image of the Larsen C ice shelf. It was an ice shelf that broke off a pretty sizable chunk of ice a couple weeks ago. It was about the size of Delaware, and it got quite a bit of media attention. You've probably seen it in the news, and really I think this media attention is with good reason, because ice sheets like the Greenland ice sheet and the Antarctic ice sheet are really important locations for understanding how regional and global sea level might change in the future. So to just sort of take a step back, what is an ice sheet? In the most basic sense, an ice sheet is really, it's a glacier, so a very dense mass of ice that flows, but it's also a glacier that is a lot larger than what we typically think of, so it's continental in scale. And what happens is, as we have these very large continental scale glaciers, they flow from the interior of the continent out towards the edges, and as this process happens, you end up getting thinning, and eventually you'll get a glacier, or an ice sheet, excuse me, that's thin enough to float, and that's what is being shown in the figure on the left-hand side. And once that ice sheet becomes free-floating, it's thin enough to float, it's now called an ice shelf, and you can see in the image, or the figure on the right, you have the ice shelf that's free-floating on top of the ocean water, and you have the ice sheet that's feeding this ice shelf from further upstream. And I wanted to bring your attention to the dashed blue line here. That's the point where the ice sheet is thin enough to float, and that's known as the grounding line. And that's really sort of what I focused on this summer, and I'll explain a little bit more about why a grounding line is important and why we care about how that grounding line moves over time. So I mentioned that an ice sheet flows, and that might seem a little counterintuitive initially, especially considering that we usually think of ice as a solid material in our everyday lives. Think of an ice cube. That's definitely solid. But on the scale that we're talking about here, the rheology, or sort of the flow and deformation properties of ice, actually are more like a very, very viscous fluid. And viscosity is the resistance to flow of materials. So you can think of honey as being a material with a very high viscosity, and room temperature water as being a material with a lower viscosity. But to sort of orient you just a little bit about exactly how viscous we're talking here, an ice sheet and an ice shelf generally have viscosities that are about 14 orders of magnitude more than honey. So we're talking about something that's super, super viscous. So to sort of zoom out just a little bit further and think about the overall geometry of an ice sheet, ice shelf system, you have, starting at the upper right-hand side, you have the ice sheet flowing from the interior of the continent out towards the ocean. And again, it is eventually thinning and eventually will become thin enough to float. And again, the point where that happens is the grounding line. And also, ice sheets and ice shelves generally can be confined. So you have two sidewalls that are surrounding the ice shelf, and that's shown in the upper left-hand corner. And then where the ice sheet, the furthermost edge of the ice shelf is known as the terminus. And to understand really why grounding lines are important, we also have to think about what are the basic forces that are important for an ice sheet, ice shelf system. And just sort of in a very general sense, you have the gravitational driving force. If we're starting at the upper right-hand side of this figure, you have the gravitational driving force, which is essentially because of the weight of the ice. That's pushing the ice out towards the ocean. And then to counter that, you have the basal drag force, which is friction along the bed of the ice sheet. And then you also have, again, because of the sidewalls, if we look at the upper left-hand corner, you have lateral drag because of the sidewalls that are confining the ice sheet. And these sidewalls can be maybe like a fjord or a valley, something along those lines. And also another force here that's important is the buttressing force. So this is the force that the ice shelf exerts on the ice sheet, and it kind of holds back the flow of the ice sheet. So you can think of this sort of like a cork on a bottle. So if you put a cork on a bottle and you flip it upside down, the cork is tight enough, no fluid will flow out of the bottle. That's kind of what's happening here is you have this ice shelf that's pushing back on the ice sheet and limiting how much ice is flowing out into the ocean and eventually breaking off and calving into icebergs like the one I showed on the first slide. So grounding lines are really important for the overall stability of an ice sheet. As I mentioned, they give that buttressing force that limits the flow of the ice sheet out into the ocean. And what happens is if the grounding line, particularly if the grounding line retreats, you can have the shelf thinning, and then eventually it's kind of similar to loosening a cork on a bottle. So if you have a loosened cork and you flip that bottle upside down, some of the liquid that's in the bottle might spill out. And that's kind of what we're talking about here is if the grounding line shifts back, you can potentially have an unstable ice sheet that is just advancing and flowing out into the ocean. And that is important because that's ice that was once far, far away from the ocean and wasn't contributing to sea level rise. So most work that's looked at grounding lines has really been one of two sort of methods, either observational, so going out to these ice sheets, or using satellites or using other data of that type, or it's been numerical modeling, so making numerical models of how do we expect ice sheets to change and how do we expect the grounding line to change. But very little work has been done using analog models. And an analog is, in a basic sense, using a material that isn't ice but behaves like ice. And that's exactly what I did this summer, is I tried to construct a model that we can use to learn a little bit more about how exactly grounding lines can change. So in making analog models, you have an important concept of dynamic similarity. So the model that you're using has to be comparable to an actual ice sheet or ice shelf. So for an ice sheet, ice shelf system, this would mean that you have a fluid flowing down a ramp, and you also have the forces scaling similarly. So if we think back to the first slide, you have the gravitational driving force, you have the basal drag, lateral drag. So trying to maintain sort of not only those same forces, but the magnitude and ratio of those forces in our analog model. And also in terms of rheology, this would again mean a viscous fluid that flows similar to how ice flows. So this is what I spent the bulk of my summer doing, is trying to find materials that were easily accessible, but also could sort of replicate some of the same forces and rheology that are typically found in ice sheets and ice shelves. So to walk you through kind of a basic schematic of what I ended up constructing, we start at the upper right-hand side. You have a fluid flowing down a ramp, and eventually that fluid flows into water, and it'll detach. And again, the point where that detaches is known as the grounding line. And this is sort of, you can think of the part that's attached as the ice sheet and the part that's detached as the ice shelf. And again, you have the terminus, which is just the furthermost edge of the ice shelf. And this is a sort of schematic view of what I ended up constructing. And this is a photo of the actual model that I ended up making. This is a profile view. So again, you have fluid flowing down the ramp into the water. And the fluid that I actually ended up using was a mixture of shortening and mineral oil. It turns out that that has the right properties, but also is viscous enough, but also is not dense and floats. I'm sure you're familiar with oil floating on top of water. It's kind of the same concept here. And we also, again, in the spirit of accessible and cheap materials, put sprinkles in the in the fluid, and we use those sprinkles along with time-lapse photography to track sort of what's the velocity of the fluid, how's it moving, which parts are moving fastest, and other things along those lines. And to give you an angled sort of corner view, again, you have the fluid flowing down the ramp, and I've outlined the edge of the ice sheet, ice shelf system in green. And again, if we look at the bottom right-hand corner, the top view, you can see the two confining sidewalls that are similar to how most ice shelves would flow in nature. So getting to this point took a lot longer than I thought. And I think, as is often common with experimental work, it takes a lot longer than you think. To get to Crisco and mineral oil, it took a lot of trying other things that didn't work. But I do have some preliminary results. So this is about 17 minutes of an initial hour-and-a-half experimental run. And to sort of orient you a little, we can look at the upper right-hand side. This is a schematic of what you should be looking for. So again, you have the fluid flowing down the ramp. And then the point where it detaches is shown in the orange arrow. That's the grounding line. And just looking at the frames starting from frame 1, there's a minute between each frame. You can definitely see the progression of the flow, and eventually if you look at about frame 7, I would say, you can start to see the fluid detach. So this is, getting to this point, like I said, took a lot longer than I thought, but now it's really sort of the point where we can start asking interesting questions with this model, this tool that I made this summer. And to sort of give you an idea of what some potential future directions might look like, we can, one, look at hanging glaciers. So this is a photo of a hanging glacier on the right-hand side. These are glaciers that lie very steeply on the sides of valleys. And they are very important because they can cause avalanche hazards. So again, if we go back to the model that I made, you can think of increasing the slope of the ramp to simulate a hanging glacier. And then also along those lines, we can think of maybe segmenting the flow or cutting it off somehow to think about how icebergs, like the one I showed in the initial image, how those might change over time. And then we also might think of modifying the setup to be specific to a particular glacier regime. So if there's a particular ice sheet, this might be another way to learn a little bit more about it in a slightly different way. That is all that I have. Thank you, and I will take any questions. Thanks. Yeah.
So, did you see the changing grounding line? It kind of looked like in the one in your book, grounding line. Like, I don't know, do I expect it to be moving down the slope or up the slope?
Yeah. Okay. So the question was, did we see changes in the grounding line? So this is about 17 minutes, like I said, of about an hour and a half. And this is actually still pretty early on. So if we look at the whole hour and a half sort of sequence of images, you can definitely see by the end of it, it is much, much further along the ramp. So it definitely is advancing. It's just sort of looking at how, like what rate is it advancing, but also is it steadily advancing or does it kind of jump back and forth? That's sort of what hopefully we can go back and do a little bit more detailed, get a more detailed look at. Yeah, well, so I think the sort of difference is in most ice sheets, particularly I think in the West Antarctic area, you have reverse bed slopes. So the ramp would be flipped to the other direction. And so that's one potential thing you can look at is flipping the ramp and seeing how that might change. Yeah. Yeah? Mm-hmm. Mm-hmm. Okay. So the question was, how would this be modified to look at hanging glaciers and how that might change the model? So I think if we're looking at hanging glaciers, there probably wouldn't be water in the model. I think as far as I know, there has been a lot of work that's been done on hanging glaciers, and I think, models that are supposedly able to predict when that avalanching will occur. So that would be more of what we're looking at without water, just sort of a fluid flowing down a very steep incline and looking at if we have a fluid that has the same sort of viscosity and material properties as ice, or at least we think it does, how does that potentially tell us more about hanging glaciers? Yeah, thank you. Any other? Sure. Yeah, so that is another, potential direction is maybe thinking about. So I think what you're getting at is, so the question was, can we look at waves and temperature and how those might affect the model that I have? And that's sort of, we're very in the early steps, but I think that's kind of, you're getting at the fact that there's a lot of different modifications you can make. Yeah, so it's like shortening, it's like butter. So that does change with temperature. When we did our experimental runs, we kept the temperature pretty constant. But yeah, I don't know. We haven't thought too much about how temperature. It might be interesting to do. Yeah, think about. Yeah. I'm not sure. Yeah. We did. So the question was about calving. Did we observe any calving? We actually did. I had left it running for a couple hours, kind of forgot about it, and then came back, and it was very clear that it had calved. So that's sort of the other interesting thing about Crisco is we think that it has a yield strength, so below a certain amount of stress, it sort of won't move depending on depending on the ratio of Crisco and mineral oil that I had mixed. Sometimes you would get, it would just sit on the ramp. So I think that is sort of what that's telling me is it maybe does have a particular sort of threshold above which, below which you won't see any movement. Like it'll just stand there for hours. But we did see calving, yeah. Any other questions? Thank you.